Have you ever wondered why the great astronomer Johannes Kepler resolutely abandoned the ancient idea of perfect circular orbits? Based on years of highly precise observations of Mars, he discovered three fundamental laws of planetary motion around the Sun. It turns out that celestial bodies move along ellipses and constantly change their linear velocity across different segments. His famous harmonic law linked the dimensions of planetary orbits with the exact time of their full sidereal revolution.
Good day. In today's lecture, we will examine one of the most significant paradigm shifts in the history of science, the transition from an ancient, aesthetically driven cosmology to a modern, observationally grounded one. This revolution was spearheaded by the work of one man, Johannes Kepler, and his three laws of planetary motion, which provided the first truly accurate kinematic description of our solar system. Our discussion today will proceed as follows. We'll begin by examining the historical context, what I have termed a crisis of circles. From there, we will systematically analyze each of Kepler's three laws, the elliptical nature of orbits, the principle of equal areas, and the harmonic relationship between all planets. We will conclude by considering the profound legacy of Kepler's work and the new question it posed for physics. So let us begin. To appreciate the magnitude of Kepler's achievement, one must first understand the intellectual framework he was forced to dismantle. For nearly 2 millennia, Western scientific thought was predicated on the axiom of perfect circular motion for all celestial bodies. This was not merely a scientific hypothesis. It was a deeply ingrained philosophical principle of perfection in the heavens. Now, Johannes Kepler was a staunch Copernican, committed to the heliocentric model. However, even Copernicus's revolutionary system retained the ancient assumption of circular orbits. The key to breaking this impasse came from the work of the Danish astronomer Tycho Brahe. Over a period of 20 years, Tycho compiled an observational record of planetary positions, particularly of Mars, with a precision that was simply unprecedented for a pre-telescopic era. In 1600, this trove of data fell into Kepler's hands, and it would prove to be the undoing of the circular paradigm. Kepler spent years performing laborious calculations, attempting to reconcile Tycho's Mars data with a circular orbit, but a persistent, small discrepancy of just 8 minutes of arc remained. While others might have dismissed this as observational error, Kepler's faith in the quality of Tycho's data was absolute. This forced him toward a revolutionary conclusion. The data was not wrong, the axiom of circular motion itself had to be abandoned. A truly momentous intellectual leap. And this rejection of a millennia-old assumption led directly to his first great discovery, a law that fundamentally redefined the geometry of planetary motion. Here we have the formal statement of Kepler's first law. It is an assertion of remarkable elegance and power. All planets move along ellipses, with the Sun occupying one of the two foci. Let us be precise about the geometry here. An ellipse is defined as the locus of points on a plane where the sum of the distances from any given point on the curve to two fixed interior points, the foci, labeled here as F1 and F2, remains constant. Now, this is the critical insight of the first law. The Sun is not at the geometric center of the ellipse. Instead, it is located at one of the two foci. The other focus, F2, is simply an empty point in space. This asymmetry is fundamental to understanding the dynamics of the orbit. We also define a key parameter, the semi-major axis, denoted A, which is half the longest diameter of the ellipse. The degree of an ellipse's deviation from a perfect circle is quantified by a dimensionless parameter known as eccentricity, denoted by the letter E. Mathematically, it is the ratio of the distance from the center to a focus to the length of the semi-major axis. An eccentricity of 0 corresponds to a perfect circle, where both foci coincide at the center. As eccentricity approaches 1, the ellipse becomes progressively more elongated. This concept of eccentricity helps to explain why the circular model persisted for so long. The Earth's orbit, for instance, has a very low eccentricity of 0.017. Visually, it is nearly indistinguishable from a circle. However, if we examine Mercury's orbit with an eccentricity of 0.206, the elliptical nature is far more pronounced. It was the orbit of Mars with its intermediate eccentricity that provided Kepler with a deviation large enough to be undeniable with Tycho's data. The geometry of the ellipse, with the Sun at one focus, necessarily implies that the distance between the planet and the Sun varies. This gives rise to two unique points in the orbit. The point of closest approach is termed the perihelion. The point of greatest distance is the aphelion. The line connecting these 2 points, which passes through both foci, is known as the line of absides. This variable distance is crucial for the second law. Having established the static geometry of the orbit, we now turn to the dynamics of the motion itself. Kepler's second law addresses the velocity of the planet as it traverses its elliptical path. The second law, often called the law of equal areas, is stated here. Consider a line segment, the radius vector, connecting the Sun to the orbiting planet. As the planet moves, this vector sweeps out an area in space. The law asserts that this vector sweeps out equal areas in equal intervals of time, regardless of where the planet is in its orbit. Let us visualize this. When the planet is near perihelion, the radius vector is relatively short. Consequently, to sweep out a given area, area A, during a fixed time interval, delta t, the planet must traverse a comparatively long arc length along its orbital path. The resulting area is short and wide. Now consider the planet near aphelion. Here, the radius vector is long. To sweep out an area, area B, during the same time interval delta t, the planet needs to traverse only a short arc length. This results in a long, thin area. The core statement of the second law is that these two geometrically distinct areas, A and B, are precisely equal in magnitude. The physical implication of this geometric law is profound and unavoidable. Since the arc length traversed at perihelion is greater than the arc length at aphelion in the same interval of time, the planet's orbital velocity cannot be constant. It must be at its maximum at perihelion and its minimum at aphelion. The planet continuously accelerates as it approaches the Sun and decelerates as it recedes. The first two laws pertain to the characteristics of an individual planet's orbit. The third law is of a different character entirely. It is a unifying principle. It establishes a precise mathematical relationship that governs not one, but all orbits within the solar system, revealing a deep, underlying harmony. This law, which Kepler himself referred to as his harmonic law, connects two fundamental orbital parameters, the sidereal period of revolution, t, which is the time for one complete orbit, and the semi-major axis, a, which serves as a measure of the average distance from the Sun. Expressed mathematically, the law states that the ratio of the squares of the periods of any two planets is equal to the ratio of the cubes of their semi-major axes. This proportionality is constant for all objects orbiting the Sun. It provides a powerful predictive tool. Given one parameter for a planet, we can determine the other relative to a known orbit. The proportionality can be simplified into a direct equation by a judicious choice of units. If we defined our unit of time as the Earth year and our unit of distance as the astronomical unit, or AU, then for Earth, both t and a are equal to 1. The constant of proportionality becomes unity, and the law takes on this remarkably simple form: t squared equals a cubed. This table provides empirical verification of the law using observational data. By definition, for Earth, a cubed and t squared are both 1, but observe Mars. Its semi-major axis of 1.52 AU when cubed yields 3.51. Its period of 1.88 years when squared yields 3.53. The agreement is remarkable. We see the same for Jupiter, where the values are approximately 140.6 and 140.7. The law holds throughout the solar system. Finally, let us situate these laws within their proper context in the history of physics. What is the ultimate nature of Kepler's contribution? In essence, Kepler provided a complete and accurate kinematic description of the solar system. Kinematics is the branch of mechanics concerned with describing motion without reference to the forces that cause it. His laws perfectly describe how the planets move, in ellipses with non-uniform velocity governed by the law of equal areas, and with their periods and distances linked by the harmonic law. Yet, for all their power, Kepler's laws are fundamentally descriptive, not explanatory. They answer the question of how with unparalleled precision, but they do not address the question of why. Why are the orbits elliptical? What physical mechanism causes a planet to accelerate at perihelion? What is the nature of the force that maintains the celestial harmony? Answering this profound question of why would be the monumental task left to the next generation and to one individual in particular, Isaac Newton.
Thank you, friends. Strive for understanding and become wiser. See you soon.